This is the fourth video for homework number 7 for Math 107. So I'm going to write again, just for contrast, the formula for the arithmetics series. So this is the sum over an arithmetic sequence. So this is how many terms you're going to go over. N is the number of the first n terms. You look at the first one that you want to add, the first term in the sequence, and the last term that you want to add. Multiply by n and divide by 2. Here it is for a geometric. A is the leading term of the sequence, minus a times r raised to the n. R is a common ratio over 1 minus r. Okay, you've got a movie theater with 24 seats. Each row back has one more seat. And there are 20 rows. How many seats are there in the entire theater? All right. If you look at the sequence of the number of rows, the number of seats in each row, starts at 24, then goes to 25, then goes to 26, then goes to 27, on and on and on. Okay? For 20 of these rows. This makes an arithmetic sequence. What's the common difference between these? The common difference is 1. Right? So you want to add 20 rows. So you're taking the sum over 20. Using the formula, here's the formula for arithmetic sequence, is n times the first one you want to add, the last row, the number in the last row, divided by 2. Okay, this is fine. The 20 goes here. The 2 goes here. The first number is 24. Now the question is, what's the last? Right? You could write all this out and try to add it. If you write all this out and add it together, you get another minus 1. I want to see you use this formula. Right. So now the trick is to figure out how many seats are in the 20th row. Here is the formula, the recursive definition for an arithmetic sequence. The nth term is the first term plus the common difference times n minus 1. So that will give you your last term that will go in here. You can work that out. In this case, you want to know the 20th row, so this n will be 20. And a1 is your 24, and what's the common difference? The common difference is 1. In the chapter on exponentials, we computed interest as though it was continuously being accrued, when with compound interest it is not being continuously accrued. It's not added into the account until the end of the compounding period. That really makes a sequence, right? It's not continuous, it goes in steps. Right? The other idea in this problem is that most of the time we started the counters at 0. Anyone going into programming, computer science, you'll find in C and C++, you start the counter at 0 instead of at 1. Oh, I'm sorry. What did I say initially? Okay, we usually start the counters at 1. But it's common in computer science and databases to start the counter at 0. So this is practice in starting the counter at 0. So a to the 0 is the first term. So you have an amount that you put in the bank, A0, right? At the end of this is compounded annually at 6% interest. Okay, at the end of the first year, so this is the beginning, here's the end of the first year. Year number 1, how much is in here? It's the amount you had plus the interest you accrued on it, which is A0 times 0.6. All right, which is the same as A0 times 1.06. At the end of the second year, you have this amount, so you have your A0 times 1.06. But then you've got 6% interest charged on that, and so you have it times another 1.06. So that's A0, your initial amount, times 1.06 squared. And now you can see the pattern from there. It's a geometric sequence. in this problem, well, this is a problem in which kind of stresses the point that you should always make a sketch before starting any problem. Anyone going into physics, engineering, even economics, biology, whatever you're going to go into, if you can make a little sketch of what you're doing, often your problem is half solved. So I'm just going to make a little sketch here, and then we'll go on. So here is the height from which you have your super ball. So it starts up here, and now you drop it. It goes down, and it comes back up. What does it come back up to? 95% of h. So this is 0.95 h, right? Then it goes down, and it doesn't know about the initial height. It just knows what it fell off to. So this is 0.95 h, but you only get 95% of that, another 0.95. You go down, and it comes back up. So now you can work it out from there. I'm going to prove these two in detail here. One of them will be on the final. Okay, now we have to prove by induction this formula. So there's several steps in proving by induction. In the first step, you set n equal to 1, and you find out if that's true. If it isn't true for the first one, you can just stop. So n equals 1 means I pick the first term here, and I substitute n equal 1 into the other side. So that will give me 2, and I want to know, is that equal to 1 times 1 plus 1, which is 2, and the answer is yes. So that's okay. Now I proceed to the second part. In the second part, I make an assumption. And in this assumption, I say it's true for a specific case when n equals k. So I'm going to change the counter to k and say this is true. So I'll write it like that, 2 plus 4, because I want to prove it in general. And you could leave the counter at k, but this is how it's done. All right, k times k plus 1, and I'm going to say that's true. Let's say out of all these cases, because n could have any number, any real number, or I'm sorry, any in case any positive integer. So that's an infinite number of terms. Let's say we find one that's right, which we're going to call k. Now the question is, can we use this to prove that it's also true when n is k plus 1? So substitute k plus 1 into this formula, and it gets a little bit tricky, so I'm going to put the k plus 1s in red, plus 6, plus on and on and on, 2, and now I put the k plus 1. Equals, and now I have k plus 1 instead of n. You can see the n's in the formula and the k plus 1s. And now there's another n here, so I have to again go put k plus 1. Give yourself enough room on a bigger piece of paper if you need. Okay, see the n up here? There's an n, there's an n, and there's an n. I replaced it by this k plus 1, k plus 1, k plus 1. Now at this point, there's often an intuitive trick that you use, and then it becomes just algebra. So the intuitive trick I'm going to use on this one, it doesn't work for all of them, but it will work for the two proofs that I show you, is that you can notice that because you're counting up, that all the terms from here up to right before here would be the same as these terms, because the k term came right before the k plus 1 term. Alright, so I know it equals that, so I replace all these terms that I've circled with k times k plus 1. So here I have k times k plus 1, because I said that's what it equaled. I said that was true, plus, there was really a plus sign in here, okay, 2, and here's your k plus 1, which I really don't need to have in red anymore, but I've left it that way. And now what have I got over here? I can do a little bit of arithmetic. I've got k plus 1 times, and this would be k plus 2. I'm doing the arithmetic. Now it is just algebra, just arithmetic. Work these terms all out. So I have k squared plus k plus 2k plus 2. I should have put question marks here on the equal signs because I'm not sure yet. Alright, on this side, well, sometimes it's more elegant to just work one side and show it equals the other, but you can work one side against the other. I'm going to go ahead and multiply this through, and I've got k squared plus, and if I add those coefficients, I get 3k for the cross terms, and then 2. Okay, let me add these up. K squared plus 3k plus 2, which indeed is equal to k squared plus 3k plus 2, and it's proved. Now I'll do one more. So the first step in proving by induction is to prove it when n equals 1. When n equals 1, I go to this side and pull off the first term, and over here I substitute 1 into this side. Okay, that's okay, fine. Now I go on to the next step. In the next step, I assume the following is true. For n equals k, I assume that 1 plus 3 plus 5 plus on and on and on and on plus 2k minus 1 equals k squared. Okay, I assume that that is true. And I say, can I use that to prove it's also true when n has advanced to k plus 1? This is another exercise in parentheses. 1 plus 3 plus 5 plus, and I go on and on and on, plus 2, I put that in red so you can see it, k plus 1. See, now my n is turned into k plus 1. Equals, and now the n is now k plus 1. I'm looking at the next term. This is that domino business that we talk about. And I use the same trick here that I used before. So let me write that term in just so you can see what I'm talking about. I know that because I don't get to really skip any terms, that I have a term here that's 2k minus 1, right? And the next term is my 2k plus 1 minus 1 term. And this equals, I'm saying, k plus 1 squared, and again I'm hoping that's true, or I'm wanting to show it's true or false, so I'm going to put question mark here. Alright, what I've done is I've written out all the terms up to k plus 1, knowing that the term right before it was the plain old k term. K is here, k plus 1 is the next term. All of this, all the way up to here, can be replaced by k squared, because I said that all the stuff, you see it's identical, was equal to k squared. I assumed that was true. So I'm going to put that down here, so I have k squared plus, and remember you've got to use parentheses like crazy, because it, okay, that was my next term. I'm saying, is that equal to k plus 1 squared? Now you can just work these terms out on both sides. It's the easiest thing to do. K squared plus 2k plus 1. When you FOIL that, here I have a k squared. Carrying that 2 through, I'd have 2k plus 2 minus 1, k squared plus 2k plus 1, and that is equal to the other side. So it's true.